the temperature of the system of that bound state, we can get a certain boundary where the phase transition happened, and we can get that from bound to a quasi-free state of quarks and gluons. So in the beginning of the universe, when there is no composite particle like this universe we have, that today we are the composite particle, this chair, table, these are the composite particles. But at the beginning, in a microsecond universe, 1 microsecond after the Big Bang, basically quarks and gluons were freely or scattered here and there. That is the state. Now we have to reach that state, and theory is now supporting that. So what we have to we want to confirm this theory via experiment. Okay, so what we have to reach here, basically we have to increase the energy such a way that it is up to 150 MeV. It's a energy unit. So physics student must know about what about the nuclear physics people, nuclear physics students. If they read that MeV or EV is the unit of energy. So we have to get that energy of that temperature. So energy is equivalent to simply kT. That is the Boltzmann relation. So that K is Boltzmann constant, T is the temperature. As I said in that phase diagram, that we have to increase the temperature. So if we increase the energy between the collision of some particle, I'll show them, then we can increase the energy. So with the increasing of the energy, we can get that temperature where that quarks and gluons will be quasi-free. So we want to do a time travel in the back, because time is always forwarding. We want to see that era. So this is basically the theoretical description of what is quark gluon plasma. Is simply that a thermally equilibrated states of a quasi-free quarks and gluons, and they are hovering around within the dimension of the nucleus. Okay. Now what? Okay. So one more thing is that why we do want to study the QGP. That is these things you can read. That what I already said. Now we have this basic quantum chromodynamics theory in our hand. Now we have to find that suitable experiment so that we can get that soup of quarks and gluons. So how we can achieve that much energy? What we can do, we can take some protons and we can squeeze them. So much pressure we get, we squeeze them and we break their boundaries, and within that volume of femtoscale, that quarks and gluons are free. That is one procedure. Another is we heat up them. We heat up so much that within that boundary they are asymptotically free. That is another way. So what? What in the so far high energy physicist or experimentalist is doing, basically heating up the system so that the quarks and gluons will be quasi-free. And that energy density is here written is must be greater than 1 GeV over Fermi cube. That is basically there some energy scale. These are the mathematical terms. Okay. So we have to reach that energy and we have to heat up. So how we will heat up? So if I have a block of piece of some stone and in one hand, and another hand if I have a stone, then if we collide them, what will happen? They'll be heated up. There will be sparks. You get that heat or what we call fire, something like in the ancient people also they rub the two stone and get that fire. So basically, they are colliding the particles and heating up that a tiny portion of the collision zone. Here, what we do in experiment, that we collide to heavy ions. So heavy ions means having the large number of protons and neutrons. Here we take lead ion and it contains 208. Its mass number is 208. That means total number of protons and neutrons inside that is 208. What about the electrons? because lead is a neutral atom. So in experiment, what we do is strip out that number of electron. It contains 82 electrons. We have to strip one by one, and that stripping process is also complicated. So you have to put some energy and strip out one electron. In this way, you have to make 82 plus ion. Once you get the ion, you basically nullified the effect of the electromagnetic interaction, because electromagnetic interaction is there only because of the electrons. Protons and neutrons do not do any kind of electromagnetic induction within that volume. Still, protons are charged particle. They also have that electromagnetic induction, but within that region, small femtoscale, strong force is so much dominance over the electromagnetic interaction. So that's why we have to only strip out the electrons, and then we get the ion. We collide them. That process I will show pictorially. Once we collide them, this is basically the transition, how the collision is happening. With first, that quark gluon will collide each other. That will be hard scattering with one quark to one quark or one gluon to one gluon, and some energy will be, that collision energy will be dumped from there using Einstein's theory that E equals to mc square. You all know that with energy dumped there will again converted to mass. So we will get the particles, and in the detector we will collect that particle or see that particles. So from see, basically here I want to say we can only collect these particles, and we can only see through detectors, and we have only that in our hand, the collision. So collision and ending, these two are in my hand. Now we have to speculate, or we have to trace that what happened in between. Okay, so where we are doing these things are done at CERN, and it is in Geneva, Switzerland. This is a beautiful picture of science, where science has no boundaries. Okay, so what is happening, or what is there in CERN? So CERN is basically, it builds a large hadron collider. So in nuclear physics, we know there are accelerators, there are colliders. These terms nuclear physics students or physics students must know. So this is basically a 27-kilometer peripheral ring, a big two ring. These two rings, there are two rings basically. So two circular synchrotron, basically synchrotron terms is also, you know that these two accelerators are there, and we run the particles through these two circular rings, and these points, like these pink points, red points, green point, and the blue point, these are the points where we cross them, like they are circulating the rings, two rings parallel. Now they are parallel, the rings are parallel. Here the ring is parallel, two paralleling, but at here that is we crossed, and while crossing they are colliding. And how the detectors are seated here in these points, the particles are coming out, that is because of the energy to mass Einstein relation, as I said. So the particles are collecting here through the various detectors. What I did, or whatever I am doing, or I am associating with Alice collaboration, ALICE, that is the pink point, and where we can do that collision. So where is Alice? It is in the surface. No, it's inside or beneath the surface. There is Mount Jura, there is Geneva Lake, and in between that there's 27 kilometers circumferences this ring, and below 100 meters you have to go down using a lift to 100 meters, and you'll find your detector. So detectors even in the tunnel are situated under the 100 to 150 meters beneath the surface. The experiments are done here, and you see that these experiments are using radioactive elements. So much radiation are there. So you have to get the so much precaution. You have to take the so much precaution to get inside the detector or to see the detector. Okay. So here is a list of accelerators from 80s to now, and LHC is still now the biggest accelerator, Large Hadron Collider. Before that, we have some other accelerators, and with the increasing energy, we have now LHC, and it is going up to 5.5 TeV, whereas other collider experiments were done in the GeV scale. Okay, so this is just to give you a brief idea that what is the collision energy. So we are increasing the energy, so that in the phase diagram what I showed you, that we have to go to that specific temperature scale. Okay, so that this ring looks like this. So this is basically accelerators what we made up of using electric field or electric quadrupoles and magnetic quadrupoles basically. So electric field gives the energy to circulate them, to accelerate the ions, to accelerate the photons. And what are doing the magnets? These magnets are superconducting magnets. So they are cooled at the temperature minus 20 degrees C, minus 250 degrees C. So this is so much complicated that you have to get the superconducting state. Still, we are searching for the room temperature superconductor. So here up to 8 Tesla we can get the magnetic field, and these magnets are basically doing the bending because it is circulating. So basically you have to bend the beam. So that bending is doing using that magnets, and we have the Lorentz formula, famous Lorentz formula for that. Okay, so how big these detectors are? In that points, as I said, the dimensions are you can see that 46 meter, 25 meter. These are big detectors, and they are so much weighted detector. The like wazn for Alice detector, it is much heavier than the Eiffel Tower itself. Eiffel Tower is made up of only iron, and Alice detector is much heavier than that. So you can understand that it is not easy to go 90 meters down, 100 meters down, and place these things. Okay, so now these experiments are basically I have some basic targets like Atlas CMS. They are basically doing the testify the quantum chromodynamics theory. Alice is targeting the quark gluon plasma. That is what I am going to present here. So LHCb, they are basically going some other physics, B physics, that is beauty quark physics. LHCb, LHCF is also some other physics. So these experiments are also have different targets, and I'll show you at the end the biggest achievement of Atlas and CMS together. Okay, so these are the rings. This is basic physics, simple physics. That the rings are there, synchronous rings are there. Particles are accelerating using electric field, and at the junction point where the detectors are sitting, we are bending them using magnets. And after the collision, one bunch of photon, like for example, one bunch consists of 10 to the power 5, 10 to the power 6 protons, and then we can cross them. The protons will collide or heavions will collide, and after the collision, you know the stages. Then the particles will come. Right. So this is basically some mathematical data. Okay. So now how the detectors look like. Here I am presenting the Alice detector in front of you. I am a collaborator of Alice experiment. So this is basically the Alice detector setup. Here the figure you can see there are two people in this figure, and they are so much tiny with respect to the detector. So detector is so much big. So anyhow, this detector is a composite detector. It is made up of many other detectors. Like if you want to study the quarks and gluons, you need, and also there are gammas, there are electrons are coming. So you need different kind of detectors. Nuclear physics, we have read many kind of detectors. So there are so many detectors and a composite detector. Okay. So what India is doing here, in Alice collaboration, India, 14 institutes, including IITs, ISAR, NISAR, etc., and research institutes, and even some university also, Delhi University is one of the example, Guwahati University one of the example. There are 14 institutes are involved in that experiments, and there are 127 members. Maybe the members are increased already because this is previous data. Okay, so how the collisions look like? This is the event. This is called the event display. This display is showing the number of tracks in the hitting the detectors. Basically, the charge particle hitting the detectors. So these are the tracks. These are the particle we are basically measuring. So you can see that so much particles are there in a single collision. Okay. These are the two different collision, PP and proton lead. That is proton and proton lead, and you can see the number of tracks are less. So you see that the ion consists of different large number of protons. You have a large number of tracks. Okay. So where do you see these pictures? You see these pictures in the Alice run control room. You can see here the scientists are sitting and they are basically controlling the collision. How this high energetic collision particles are moving at the almost speed of light. So they are controlling that beam and they are colliding them. So after the collision, basically a beautiful picture show that the first the QGP state is there, then QGP from quark gluon plasma, they are coming to the hadron state, and the hadron state, then they are coming after some collision, the hadrons called hadronic collision, reach to the final detector. So we have to find that that particles. We have to calculate that behavior of the particle or the physics behind the particles. So this is a beautiful space-time evolution diagram. This is simple Minkowski's diagram what we read in our physics. That is the space and time axis, simple Z and T time axis. Here there are two parallel collisions are showing. One is proton-proton, one is heavy ion. You can see the simple difference. There is a QGB or quark gluon phase state here. In the left side there is no. So we compare these two states or these two collisions and we confirm that the quark gluon plasma soup is happened there. Okay. So before going to the results or confirming with the calculations, we need to know a little bit mathematics. There is a mathematical term called the impact parameter, and that is basically these two disk type ions, they are colliding, and the distance between these two center is called the impact parameter. Now depending on the impact parameter, the collision range will change and the number of particles production will now change. Now how we will find the QGP is there. There are so many observables listed here. Some of them I will describe here and give you that proof that quarks and gluons are really the plasma happened at the beginning. Okay, so here we see some Alice results, and this is charge particle multi-state. So once the particles are detected in the detector, we can find that how many numbers of particles are coming per collision. So here almost 2000 number of particles, only the charge particles we are counting here, and this is a large number of particles we are having in a collision. You can see that picture also showing that n part is basically signifies that. So with the increasing energy, we can also have large number of particles. Now how much energy we are expecting? This is the energy scale, and that is the Bjorken energy density. And there are many modifications in the detectors. These are the one of the sketch. And this is the beautiful timeline from 2021 2014. So it's a 20 years of already futuristic plan is there. Students who wants to join Alice collaboration have a bigger future in the experimental high energy physics, because we can confirm that 2041 we will have large number of data. You can do your experiment, you can do your research enormously, right? Okay, so now I'll conclude with the biggest success of the LSC, that is the Higgs discovery. You probably know that is called the God particle, right? So God particle, which is giving a mass to all the quarks. This is the celebration at CERN. It is in 2012, and Peter Higgs got the Nobel Prize in 2013. This is like paper cuttings and media also covered throughout the world, including India. There are so many papers you can see, and it is the biggest success, and it is coming from Atlas and CMS experiment. So this is basically what I conclude here. And confirming that our experiments has successfully achieved that microsecond universe and recreated the universe once again. Thank you so much.
So, audience, your future is secured up to 2041, and the positions are there to grab. Thank you, Dr. Somnath, for your enlightening lecture, enlightening us about our very existence, and you have explained a very complex matter with such clarity, showcasing your expertise over your topic, your field. Now, I would like to ask audience if you have any queries. This is the time for you to interact with Dr. Somnath. Please. Anyone have any questions? Yes, one, please. Okay. बिल्कुल बिल्कुल आप बिल्कुल पूछ सकते ओके 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 गो ऑन ओके ओके
हाँ अच्छा सर मेरा एक क्वेश्चन है सर कि सर क्वार्क सर चार्ज है या नहीं है उस पे चार्ज
क्वार्क में चार्ज है
क्वार्क में चार्ज है तो सर प्रोटॉन पे जो सर
बट दैट चार्ज इज नॉट द कन्वेंशनल चार्ज दैट इलेक्ट्रॉन में जो चार्ज है ना वो चार्ज क्वार्क में नहीं है उसको हम लोग कलर चार्ज बोलते हैं वो अलग क्वांटम नंबर है थोड़ा
सर ये
तो
कलर चार्ज क्या होता है सर
कलर चार्ज मतलब जैसे सिंपल वे में अगर समझाने की कोशिश करें इलेक्ट्रॉन है एक इलेक्ट्रॉन और दूसरा इलेक्ट्रॉन है दोनों हम लोग का चार्ज पार्टिकल है जो हम लोग कन्वेंशनल चार्ज बोलते हैं राइट जो इलेक्ट्रिसिटी प्रोड्यूस करता है ठीक है उसमें जो इंटरेक्शन हो रहा है दैट इज कॉल्ड इलेक्ट्रोमैग्नेटिक इंटरेक्शन एंड इलेक्ट्रोमैग्नेटिक इंटरेक्शन किस वजह से हो रहा है दिस कन्वेंशनल चार्ज बट मुश्किल ये है कि जो क्वार्क्स है उसमें इलेक्ट्रोमैग्नेटिक इंटरेक्शन हो नहीं रहा है ठीक है तो उसमें जो इंटरेक्शन हो रहा है उसको हम लोग नाम बोलते हैं स्ट्रॉन्ग इंटरेक्शन अब थियोरेटिकली पीपल जब थ्योरी बना रहे थे तो उनको सिमिलर पैटर्न में उसको एक्सप्लेन करने के लिए कुछ टूल चाहिए था तो उन्होंने क्या किया कलर चार्ज के नाम से उस चीज को एक्सप्लेन करने की कोशिश की इन सिंपलेस्ट इतना ही बता सकते हैं क्योंकि इसके बाद थ्योरी बहुत कॉम्प्लिकेटेड है
एक इसमें और था क्वेश्चन सर कि मतलब इसमें कोई बुक में मैंने देखा था न्यूक्लियर फिजिक्स में कि सर प्रोटॉन जो है उसको आप क्वार्क में कन्वर्ट कर सकते हैं इधर
मतलब प्रोटॉन का अंदर क्वार्क है कन्वर्ट नहीं कर सकते
आप और डॉन क्वार्क में आप कन्वर्ट कर सकते हैं
क्वार्क में कन्वर्ट नहीं कर सकते
मतलब उसी से मिल के बनता है सर वो
उसी से मिल से बनता है
जी और एक न्यूट्रॉन भी लेकिन सर इलेक्ट्रॉन के बारे में क्वार्क का कोई जिक्र नहीं किया कोई रिलेशन नहीं था सर उसमें
इलेक्ट्रॉन न्यूक्लियस के अंदर है ही नहीं तो
मतलब आप क्वार्क का चार्ज सर +2
अगेन चार्ज जो क्वार्क का है वो कन्वेंशनल चार्ज नहीं जिससे इलेक्ट्रिसिटी प्रोड्यूस हो रहा है वो इलेक्ट्रिसिटी नहीं बना सकता
तो सर 2/3 E जो है सर
ये फ्रैक्शनल
अच्छा
ठीक है सब ये सब यहाँ पे हम लोग क्या चाहिए 1 चार्ज 2 चार्ज ये चार्ज वो जो 3/2 2/3 ये सब करने से क्या हो रहा है हम लोग न्यूक्लियस का चार्ज जो प्रोटॉन का +1 चार्ज है उसको निकालने की कोशिश कर रहे हैं तो दिस इज वेरी मच रिलेटेड टू that is not a 1 charge that is 2/3 charge that is fractional thing so वो जो चार्ज है that is basically जो चार्ज इलेक्ट्रॉन कैरी करता है तो वो चार्ज उसको गवर्न नहीं करता है तो कलर चार्ज उसको गवर्न करता है
कंफ्यूजन नहीं था सर कि सर ये फिर क्वांटाइजेशन के लॉ को वायलेट कर रहा है
नहीं कोई क्वांटाइजेशन नहीं बिकॉज दो थ्योरी डिफरेंट है इसमें हम लोग क्वांटम जो हम लोग क्वांटम क्रोमोडायनेमिक्स ले रहे हैं जो थ्योरी स्ट्रॉन्ग इंटरेक्शन गवर्न करेगा उसमें आप इलेक्ट्रोमैग्नेटिज्म का जो भी थ्योरी है आपका नॉर्मल चार्ज का जिसमें हम लोग क्या बोलते हैं जो इलेक्ट्रोस्टैटिक इंटरेक्शन हम लोग ये जो फॉर्मूला यूज करते हैं वो सब यहाँ पे नहीं होगा क्योंकि आपके पास वो जो 2/3 चार्ज है दैट चार्ज डजंट डू एनीथिंग दैट इज जस्ट सिंपली गिविंग द प्रोटॉन का चार्ज जो प्रोटॉन का चार्ज है ना वो तो सिंगल चार्ज है +1 है उसका चार्ज कैसे डिफाइन करेंगे तो उसके लिए वो 2/3 चार्ज है
बस वही चीज सर एक वन मोर क्वेश्चन
जी जरूर
सर LHC का जो सर डिस्कवरी हुआ था शायद 16 में सर एक मैगजीन मैंने पढ़ा था ड्यूरिंग ग्रेजुएशन LHC लार्ज हेड्रोन कोलाइडर के बारे में, तो सर उसी समय गॉड पार्टिकल आया था सर, लास्ट में आपने जिक्र करा सर। वो सर गॉड पार्टिकल जो था सर वो मतलब ऐसा पार्टिकल था कि मतलब हाईली एनर्जेटिक।
No, no, no. It's not that high. Even pop quark has much more. Pop quark का जो मास है ना वो 170 में है. हिग्स का जो मास है 125 में. हिग्स लेस है.
इसको सर गॉड पार्टिकल क्यों बोला गया था सर?
इसलिए क्योंकि हम लोग विश्वास करते हैं कि गॉड ने सब कुछ बनाया. दैट्स व्हाई मैं पिक्चर वो दिखाया कि एक जो हमारे यूनिवर्स वो गॉड्स क्रिएशन है. क्योंकि जिस चीज को हम लोग एक्सप्लेन नहीं कर सकते साइंस में उसको हम लोग बोलते हैं ये भगवान ने बनाया है ना. तो इसीलिए उस चीज का नाम दिया गया गॉड पार्टिकल. जबकि टॉप क्वार्क का मास अगर 170 MeV है और हिग्स अगर 125 MeV है तो टॉप क्वार्क का मास हिग्स कैसे दे सकता है? पूरा का पूरा मास नहीं दे सकता. दैट्स व्हाई इट्स अ गॉड पार्टिकल, but still the most of the mass that creation is coming from the QCD field, that is the associated.
अभी तक सर ये तो मिस्ट्री बना हुआ है सर कि मतलब वो पार्टिकल फिर उसके बाद आया नहीं सर 16 के बाद,
वो
पार्टिकल में भी नहीं आया.
ये थ्योरी था 1967 का पीटर हिग्स का जो कंफर्म हुआ अब. तो यू अंडरस्टैंड दैट साइंस एंड टेक्नोलॉजी जैसे LHC जैसे जैसे बिल्ड हुआ, मतलब जैसे एक्सेलरेटर बिल्ड हुआ, जैसे जैसे हम इंप्रूव करते गए तब जाके हम लोगों को सिग्नल, टाइनी सिग्नल मिला. मे बी आई हैव द पिक्चर. हाँ हियर जो तुम ये जो आप पिक्चर देख रहे हैं यहाँ पे आप देखिए वो जो बैक ये लाइन जो है ये लाइन बैकग्राउंड है और उसका वो जो छोटा सा है ना दैट इज बेसिकली सिग्निफाइज दैट सिग्नल. तो इसको ढूंढने के लिए इतना कुछ मेहनत करना पड़ रहा है इन लोगों को. तो दैट चैनल इज हिग्स टू गामा गामा एंड दैट इज द ओनली डीके चैनल दैट कन्फर्म्स दैट ये उतना सा मिला. तो इससे ही प्रूफ हो गया. बट वंस अगेन जो पब्लिक को पता है, हम लोग फिजिसिस्ट है, हम लोग को जेन्युइन पिक्चर पता होना चाहिए. हिग्स जो है वो देता है मास.
हिग्स,
यस हिग्स देता है मास बट हिग्स पूरा मास नहीं देता. इट्स ऑल अबाउट द QCD फील्ड. जैसे इलेक्ट्रॉन का फील्ड है ना, इलेक्ट्रॉन का जो चार्ज है वो कैसे बनता है? इलेक्ट्रॉन एक इलेक्ट्रिक फील्ड रेडिएट कर रहा है ना, वो इलेक्ट्रिक फील्ड कैसे प्रोड्यूस होता है? वो वैक्यूम से प्रोड्यूस होता है. इलेक्ट्रॉन एंड पॉजिट्रॉन पेयर जो है वो गामा निकालता है. इलेक्ट्रॉन और पॉजिट्रॉन एनिहिलेट करोगे तो गामा निकलेगा. गामा ही जो है जो बेसिकली फील्ड है, जो इलेक्ट्रिक फील्ड हम लोग जो हम लोगों का इक्वेशंस है, राइट. तो ये है. तो बेसिकली यहाँ पे थोड़ा कॉम्प्लिकेटेड सिनेरियो है बट दैट इज स्टिल मिस्ट्री है. ये हमेशा मिस्ट्री रहेगा.
थैंक यू सर. थैंक यू.
Thank you for your question. Thank you, Dr. Kaur, for answering his questions.
India is not building. India is building. India already built a few detectors. That is one of the part of the Alice detector, total composite detector. So that is one of the detector is called photon multiplicity detector, PMD. That is complete India's contribution. कोई other country इसमें involved नहीं था. But that is now over. PMD over हो गया. अभी दूसरा detector में India involved है. इंडिया जो आप बोल रहे थे मे बी न्यूज में जो था वो है एक न्यूट्रिनो डिटेक्टर कंप्लीट जो इंडिया बनाने की कोशिश कर रहा था. बट बिकॉज ऑफ द पब्लिक एंजाइटी, क्योंकि पब्लिक को लगता है कि ये रेडियो एक्टिव चीज अगर हमारे यहाँ आएगा तो लोग मर जाएंगे, तो इस चक्कर में जहां पे साइट पे वो बनना था वो बेसिकली तमिलनाडु में बना था. पहले दार्जिलिंग साइड में बनना था, बंगाल के साइड में, फिर तमिलनाडु में साइट डिसाइड हुआ. बट गवर्नमेंट उसको इस एक्सरसाइज को कंप्लीट नहीं कर पा रहा है बिकॉज ऑफ द पीपल्स एंजाइटी. मतलब लोग बेसिकली जो साइट पे काम हो रहा है वहां पे जाकर प्रोटेस्ट कर रहा है, धरना देना स्टार्ट कर दिया. तो इट्स नॉट पॉसिबल. सो दैट्स व्हाई स्टिल इट इज रनिंग. मतलब डिग हो गया है, मिट्टी के अंदर डिटेक्टर बिठाया गया है, सब कुछ हो गया था. तो प्रोटोटाइप जो डिटेक्टर होता है वो बिठाया गया था. बट देन ऑपरेशंस कहाँ से आएगा? फंडिंग से आएगा ऑफकोर्स. अब गवर्नमेंट फंडिंग तो बंद कर देगा ना, इतना प्रोटेस्ट होगा. सो दैट्स द थिंग. So India right now India is only participating in LHC RIG, this kind of collaboration by making small contribution, and we will continue till 2041 till the LHC goal right now. So we have lots of time and lots of data, of course, to research.
Thank you, Dr. Somnath. On a similar note, on the same note, I want to ask you On a lighter note, I want to ask you one question, that whenever your experiments at LHC was started, the common people, were having a misconception that your work may lead to emergence of a black hole. Okay, now my question is that, now I know that this is a lot of this is unscientific, but I still want to hear from someone who has worked there, that what is the probability, qualitatively or quantitatively, that you people are going to throw us into the black hole? What is the actual probability that you think?
The black hole thing is complete different thing. That is actually जो the last speaker जो हमारे speaker थे IIT पटना से, उन्होंने जो थोड़ा जो theory बता रहे थे gravitational theory, तो little bit different इसलिए है क्योंकि हम लोग जो है, I can give that picture again so that I can explain. QCD जो phase diagram है, yeah, this one. Yeah, this one. So from this, अगर x axis देखोगे, that the x axis giving the need baryon density, that means it is increasing the mass. Y axis जो है वो temperature है. So LHC is running in that where need baryon density is 0. But for making a large thing like black hole, you need lots of gravitation, and from lots of gravitation कहाँ से आएगा? Need baryon density बढ़ाना पड़ेगा, मतलब mass बढ़ाना पड़ेगा. So LHC is nowhere near the black hole.
Okay, thank you for explaining that and getting okay.
Yes.
Oh, please. Last one, please.
जी कॉस्ट बहुत प्रैक्टिकल लाइफ में यूजेस, डायरेक्ट यूजेस कभी नहीं होता साइंस का. कुछ भी आप करिए, जैसे आप अगर मटेरियल साइंस भी करिए तो छोटा छोटा इम्पैक्ट होता है, धीरे धीरे दिखना होता है. तो वन ऑफ द बिगेस्ट इम्पैक्ट जो मैं बता सकता हूं अभी के लिए, सन स्टार्ट होने से बाद जो डेवलप हुआ फर्स्ट थिंग, दैट इज www डॉट, दैट इज द इंटरनेट. सो सन इंटरनेट फर्स्ट प्रोवाइड कर दिया आपको, जो वर्ल्ड वाइड इंटरनेट. सो वन ऑफ द एप्लीकेशन, राइट. अनदर एप्लीकेशन जो आप मटेरियल साइंस में हम लोग करते हैं, यहाँ पे छोटा छोटा टेबल टॉप जो भी एक्सपेरिमेंट होता है, थोड़ा बिगर एक्सपेरिमेंट होता है, जिस तो उसमें जो हम मटेरियल यूज करते हैं, सन उसी मटेरियल के एडवांसमेंट करता है. क्योंकि डिटेक्टर हम लोगों को बना रहे हैं बनाना, और डिटेक्टर कैसे बनेगा? सॉलिड से बनेगा, लिक्विड से बनेगा, गैस से बनेगा, जो हम लोग मटेरियल साइंस भी यूज करते हैं, प्लाज्मा भी फिजिक्स भी यूज करते हैं, दूसरा फिजिक्स में भी यूज करते हैं, ऑप्टिक्स में भी यूज करते हैं. सो सन इज बेसिकली गिविंग द एडवांस मटेरियल्स आल्सो. सो स्मॉल इम्पैक्ट सन से आता है. ये सब जो है, ये इटर्नल क्वेश्चंस जो हम लोग के मन में है, जैसे हम लोग स्पेस में जा रहे हैं, वहां पे हम लोग स्पेस शिप रख रहे हैं, तो पहले जब लोग स्पेस में गए या चांद पे गए थे, उसका थोड़ी इम्पैक्ट था हमारे जीवन में. बट अब नाउ इलॉन मस्क इज डूइंग व्हाट? he is giving you internet everywhere, in every village, in every pond, every tree, everywhere, because he has spanned his satellites everywhere. So you see that impact. पहले सैटेलाइट गया था उस हिसाब से नहीं गया था.
तो फर्स्ट जो गया था तो उसमें भी तो कुछ इंफॉर्मेशन मिला था, तो वो तो फायदा हुआ ही था ना.
बट डे टू डे लाइफ जो हम लोग इतना कॉस्ट, मतलब बिलियंस ऑफ डॉलर अगर इन्वेस्ट करेंगे तो वेस्ट हो गया ना फर्स्ट डे में. तो फर्स्ट डे में $1 बिलियन वेस्ट होता है, जरूर होता है, बट उसका इम्पैक्ट बाद में. आज जैसे फर्स्ट सैटेलाइट गया था तो उसमें भी $मिलियंस इन्वॉल्व थे, तो उससे क्या इन्फॉर्मेशन मिला जिससे हम लोगों का जिंदगी चेंज हुआ था? कुछ नहीं हुआ. बट देन now you see that internet is everywhere now. So that's the impact. You have to wait for the science to be impacted, because जब न्यूटन्स ने लॉ बनाया था तो उसका डायरेक्ट एप्लीकेशन नहीं होता था. धीरे धीरे अब हम लोग कार बना रहे हैं, फिर थर्मोडायनेमिक्स बना, कार्नोट इंजन बना, तो इंजन बनाए, लाइक दैट. सो साइंस ऑफकोर्स हो रहा है, ऐसे ही हो रहा है. जैसे आपको बोला ना, जो इंटरनेट प्रोवाइड जा रहा है, एडवांस टेक्नोलॉजी हो रहा है, तो ऐसे ही हो रहा है आपके जीवन में, धीरे धीरे इम्पैक्ट हो रहा है. बट यू विल नॉट नोटिस दैट इन ए लाइक सिंगल डे.
Thank you, Tripti. Thank you, sir. So just one more second, I want to take this opportunity to share my feelings. That I want to tell the audience that I have shared classroom just like you guys share with Dr. Somnath during my masters, and I mean, we talked about everything except physics for the last 10 years, and I have never noticed how we have done so well until the last night when I was trying to note down some of your contributions to construct your introduction speech, and it just filled my heart with joy and pride. I'm so happy to see you going such places, and we all would love to have you again. We all loved your lecture. Thank you very much, Dr. Somnath, for this.
Thank you so much.
So now we are going to the next part of this session. Okay. Anything, ma'am? So now moving forward to the next part of the session, we will be calling one by one the presenters, the oral presenters. Now, the first one that I would like to invite on stage is Ashutosh Kumar, OP3. Please come to the stage and give your presentation, please.
You will have 7 minutes, okay? Only 7 minutes, not more than that. This one?
सिन्हा सर ये स्टार्ट होगा please wait for a while.
Okay.
Like to felicitate Dr. Somnath first and
Then I will start with, we'll proceed with things, okay? We will call you on stage, just a minute.